Welcome. In the previous lesson we discussed the different types of collisions and how to classify them based on the behavior of kinetic energy before and after the collision. But we restricted ourselves in that particular lesson to one-dimensional motion only. Today we're going to continue to look at collisions, but we're going to look at a few multi-dimensional examples. If you look on the screen, you see an example of the first one. We're going to study a perfectly inelastic collision in 2 dimensions. Take a moment and pause the video so you can read the example. I have illustrated the example already on the screen. We have 2 cars approaching an intersection and they're going to collide and stay stuck together in an ugly wreckage afterwards. And what we want to do is figure out the final velocity of that wreckage. I think you can see, based on the initial directions of both objects, that we are going to have motion in the, if this were north, south, east, west, right, we're going to have motion roughly in the southeast direction, right, something like that. Okay, so I'll show you how to work through this. Remember, momentum is a vector, and so if you're working with multiple dimensions, you can just work in each dimension separately and then combine. So what I'm going to do is I'm going to write out the momentum conservation equation for this collision in each dimension separately. Okay, I'm going to pause and do that now. Okay, you see on the screen the equations for each dimension. Now, if we go ahead and solve for this, we are going to get the following for V1. Now remember, this V final is in the x direction, right? So I'll put x here. So this is a 6 point. That works out to that. And then in the y direction, we get actually a pretty similar speed. Okay, and I think that'll be apparent to you if you look at the numbers. So M1 is traveling faster, but it's not as massive, right? M2 is more massive, but traveling slower. And those two offset each other for probably pretty similar momenta coming in. Right, you can see pretty close. So that means that, let's go ahead and do some color coding now. That means that we're going pretty close to 45 degrees, right? Right at southeast, kind of like we were predicting. So let me go back to the diagram and put in some color-coded vectors to illustrate this more clearly. Okay, I did some color coding and wrote out the vectors by component. All right, and what we're after, of course, is the magnitude and direction of that red arrow, which represents the total momentum of the wreckage after the collision. Now remember, on this particular, this should be a momentum right triangle. So I've just written out the velocities here. So you see, you know what to do with x and y component, right? If you want the total, is you're just going to put that. So if we want the total velocity, right, we're just going to do the following. Okay, and I won't plug in the numbers here, but the result of this is 8.9 meters per second. Okay. And then, of course, remember, momentum is a vector, so we need the direction as well. So we have to do the inverse tan of the 2 components. And when we do that, we get almost 45 degrees like we thought we would. Okay, I'm running a little bit out of space here. I'll just put it right here. It works out to be 43 degrees. Okay, and that would be south of east. 43 degrees south of east. So we get a final velocity of 8.9 meters per second, 43 degrees south of east. I'm pretty sure you picked it up by now, but you saw that I converted from kilometers per hour to meters per second. I wanted us to look at the same problem from a slightly different perspective, where we can pull together our newfound knowledge of the center of mass. And because of the arrangement of the initial momenta in this problem, there's actually a slightly more elegant approach where you don't have to work quite so separately in x and y dimensions. Let's take a look at it on the next screen. I have represented the initial momenta, okay, by vectors. And even though we don't actually have diagonal motion during the initial part before the collision, we can still represent their total momentum that way, right? Because we have some x momentum, we have some y momentum. All right, and so what that allows us to do is actually allows us to write out the momentum in the following way. We can just use our unit vectors to represent this momentum. I'm going to use a little shorthand just to save some room, but in the x direction we have, say, m1 times 60. okay? And I'm going to drop the units, and that's in the I direction, right? Plus M2 40 in the J direction. That is the total momentum expressed vectorially. Now remember, we have a relationship, okay, that the momentum of the center of mass, okay, will be the total momentum times the velocity of the center of mass. So that we can do the following. We can divide the total momentum by mass to get the velocity of the center of mass. Now remember, after the collision, the two objects move together. Both objects are at the center of mass. And so we can use this relationship here. All we're going to do is divide this top thing here, right? We're going to divide that by the total mass of 4,000 kilograms. Okay, so I'll pause and write out the numbers for you. All right, so I've put some numbers in, and now, right, so we're solving for that. You can see, what you see here is the momentum, and then I'm going to divide each term here by the 4,000 kilograms. Okay, and let's work that out. Obviously, we're going to get the same result, but I can see, hopefully you can see it's a little bit more elegant. Okay, you see the result? Now the numbers don't match because I worked in kilometers per hour this time, but we can compare to the previous answer by comparing the relative magnitudes of the components. And you'll notice that they're very close to each other, right? Just like they were previously. So we're getting that angle. Now, I was a little sloppy here. Pay attention to our directions, right? That should be a minus, right? Because down was negative. And so if we go in, there should be a minus here. And then we'll have a negative component here, right? That's going to put us, that's positive comma negative, right? It's going to put us in the fourth quadrant or the southeast quadrant. All right, so there's perfectly inelastic collisions in two dimensions, how you might go about dealing with quantities in multiple dimensions. We want to wrap up with another look at elastic collisions. Okay, so let's look at the next screen. Okay, so here's an example of an elastic collision. Now we don't know anything about this collision. I've illustrated it with, essentially billiard balls. We know that in fact in real life some kinetic energy will convert to sound and heat in the collision, but we're going to assume that this is, for the purpose of this example, an elastic collision. Okay, and I'm going to show you how quickly things get more complicated. We're not actually going to work this problem out completely. We're just going to talk about how many variables there are and how we would go about solving them. For there to be a collision in two dimensions, you're going to have an off-center collision. Okay, so notice here that the center of mass of M1 as it moves toward M2. Okay, we just kind of made it line up like right there with the edge. All right. So how much it's off-center? Okay, how much the off-center the collision is? I think you'll see that that's going to affect the outcome. So we're going to need some way to measure how far off-center the collision is. Okay. Now I've also illustrated what happens after the collision, right? Both objects move with a two-dimensional velocity after the collision. So I want you to think about how many variables there are after the collision. How many variables we need to solve for? Well, in one dimension we only had two variables, right? We had V1 final and V2 final. Okay, and they were both in the same dimension. But this time we actually have four variables. Okay. And they can be illustrated in two ways. You can think of it as the x components of both velocities and the y components of both velocities, right? Those are the four unknowns. Or alternatively, okay, the magnitudes of both velocities and the directions, right? Theta 1 and theta 2 of both velocities. So if we have four unknowns, that means we are going to need four equations. And the question is, what four equations will we use? Well, these are the four equations that we will use, okay? Obviously, we're going to be using momentum conservation, okay? And we can use it in each dimension. So let me write that out, right? So we'll have in the x direction, right? So Pix equals Piy, P final, excuse me, like that. And then we'll have another equation, right? P initial in the y direction equals P initial final in the y direction. Okay, so now we have two equations, but we have four variables. Remember, we need four equations. Well, the third equation, okay, is going to be the kinetic energy conservation, right? Because we did stipulate that this was an elastic collision. Okay, so that'll be the third equation. And the fourth equation has to do with the angles, right? You need some measurement of the angles, and that's also going to be dependent on this thing right here, okay? That distance, and that distance is known as the impact parameter, okay? In your book, they use the letter B, okay? And typically, that's some information, like some numbers that you collect about the collision, okay? But the idea here is that when you go into 2 dimensions, the number of variables multiplies greater, okay? So like I said, we're not going to solve this problem completely. However, there's a special case scenario of a 2-dimensional elastic collision that has a nifty outcome or solution, and we want to look at that, okay? Let's take a look at it here on the next screen. Okay, the special case is this. The objects are of equal mass, and the second object is initially at rest. Okay, so I've drawn the before and the after here. And there's some interesting things that come out of this. Okay. The first is that when this happens, okay, what you're going to find is that the momenta or the velocities of the 2 objects afterwards are actually going to move at right angles to each other. Okay, like that. And this can be proven. They worked this out in the book using kinetic energy conservation. But watch what happens here. We can rearrange these vectors. Okay, so this is the initial momentum, right? So I'm going to pull that down here. By momentum conservation, right? P initial equals P final. Okay. Well, vectorially, right? We have 2 final vectors, right? We have P1 final and P2 final. Right? Now, vectorially, remember when you add vectors, you put them head to tail. So watch what this works out to be. Okay, here's P1 final, and here's P2 final. Right? And you can see that vectorially, they now add up to the initial momentum. All right, and that allows us to come up with a mathematical relationship that relates to that triangle. Okay, it relates the velocities to each other, and that's simply the Pythagorean theorem. Okay, applied to this triangle. Right? The Pythagorean theorem applied to this triangle. Okay? So that's the special case scenario solution, right, for the time when we have the second object at rest and then they're of equal mass. That makes things a lot simpler. All right, there you have it. Collisions in 2 dimensions.